Hello and welcome everyone. Today let's discuss the tree data structure. So a tree data structure is a non-linear and hierarchical data structure, and it sort of looks like this. If you recall from our intro to data structure, where we talked about the linear data structure and the non-linear data structure, linear follows a straightforward linear kind of like structure, but non-linear can be haphazard, like graphs. Think of your Google Maps, your graphs, or a tree, right? A literal tree. We discussed the arrays data structure, linked lists, doubly linked lists, stacks, queues. These are all linear data structure. As you can see, they follow this structured linear flow. But once we think of a tree looks like a real tree. Picture any tree that you I've seen before. Now flip it upside down. This is what a tree data structure looks like. And we saw that examples of tree data structure, like practical implementation of them, is the HTML DOM, that's the document object model. If you have ever looked at your developer tools in whatever browser of your choice, I think Chrome is a popular choice. When you have the HTML, the head, the body, the list, and all of your tags and semantics that you use to write your code is structured in a tree format because one is dependent on the other. There has to be an HTML because before there can be an head. The head the head is separate from the body. Now the body contains what you want the content of your page to be. And then we also have the file system. When you look at your computer, if you had played around with um your command line interface, your command line tools at any point, then you would see that you're navigating from one structure to the other, going in and out of it. That's a file system also uses the tree data structure. Then more literally, an hierarchical structure. Let's think of family. You have your father, the mother, the siblings, the children, your cousins, your grandparents. In fact, when we start discussing the tree terminologies, you would see that trees have all of these things, right? But when we talk about hierarchy system, you can readily think of a company structure, the board of directors, the CEOs, the CFOs, the HRs, the marketing directors, and everyone else in the company. Now let's discuss some tree terminologies. The first thing we're going to discuss is a node. A node is something that you will commonly hear talked about in a tree. A node, and a tree is a collection of nodes. When talk about nodes, you can see the highlights in the images in the blue highlights. They are called nodes, and it's a square bracket because I want to visually represent that a node contains three structure: the left child, the value, and the right child. And what does this even mean? If when you think of a tree, right, a tree has its branches, its roots, they are all connected to the tree. Now the branch has leaves attached to it. Now the leaf is then attached to the root of the tree. In data, we represent this as a container that has a left child, a left reference, a value, and a root. So let us go back to our hierarchical method. So we're going to say that okay, we have the CEO, the value is probably his name or his identity, his address, and every detail about him. Then the left child will be the address to the next thing that is pointed to. After the CEO might probably be like the CFO, the CTO, and on the right child can probably be like the HR, the next subordinate after it. So when you think of a node, the node structure encompasses the left child, the right child, and the node. And this is structurally represented in a code as a class, mostly an object model. And a class of node would have its data, what it is about, then it would have references to its left child and right child, because remember, a tree is a collection of nodes and these nodes are connected to one another. And how do we find these connections? Through its addresses from the left to the right child. Next, we have the edges. The edges are the connecting links between nodes in a tree. Now we've already discussed that a tree is a collection of nodes, right? Now, how are these nodes connected? They are connected through their edges. They are connected, and once you break off the edge, you can know that okay, this tree no longer exists. Now, let us have a quick trivia. How many edges do we think are in this tree? You can pause this video now and give it a quick spin. So we have one, two, 3, 4, 5, and 6. We have 6 edges in this node. We also have the parent and child node. Now, I told you that the three terminologies will be very similar to family structure. Now, when we talk about the parent node is any node that has a connecting child, and they are highlighted in yellow to give us a feel of what that looks like. It just means that, okay, if I have a child, then I am a parent. And we can see that there are some nodes that are not highlighted, and these are because they have no children, therefore they are not parents. Sorry. Then we have the children node. Children node are nodes that have parents, right? And we can see that every node in a tree is going to have parents apart from the one that birthed them, and that is also called the root node. The root node is the beginning node, is the node that birth every other node in a tree. And we also have the leaf node. Leaf nodes are basically nodes without children, highlighted in brown, and nodes that do not have children, and they are called leaf nodes. Next, we have ancestor nodes. Ancestor nodes are, when we talk about parent and child nodes, there are some nodes that are not direct children of a parent's node, but they still have some link, just like how your grandparents, they are not your direct parents, but they are the parents of your parents, so they are sort of like your ancestors, right? Because they have some connections to you. When I start to trace your genealogy from you to your parents, I can reach them, right? And what are the common ancestors between 5 and 6? Common ancestors means that something that a similar ancestor that they have in common. Can you try this out on your own? And if you chose one, the answer is correct. Think of you and your cousin, right? You both do not have the same parents. 5 and 6 parents are 2. 5 parents is 2. 6 parents is 3. But you and your cousin have the same grandparents, and that is your common ancestor. Cool. Now let's look at the descendants node. The descendants node are just like how you are your grandparents. Your grandparents are your ancestors, then you are definitely your grandparents' descendants. Basically, they don't have a direct link to you. Like, it's not like your parent child where there is this straight up link that we can see, but they are connected to you through genealogy. And we have this in the tree structure too. All the nodes that you have access to from the parents down to the child are called the descendants nodes. Quick trivia: is 5 a descendant of 3? Give it a spin. Let's see what you get. No, 5 is not a descendant of 3, because there is no way to access 5 from 3. So giving the analogy of you and your cousin, you are not a descendant of your aunt or your uncle. You are definitely neighbors, you are definitely related. We have that terminology in trees, but you are not a descendant of them. You have more like a parallel relationship. You cannot reach your uncle if you are going down a straight path from you to your parents, then to your grandparents. There is no point where you are going to be directly connected to your uncle or aunt. There is not that connection, but of course there's relationship like siblings and neighbors and all of that. And we have the sibling node, and the sibling nodes are children with the same parents. This is straightforward. Then we have levels in a tree. Levels in a tree are described by how many edges that there are in a tree. And the levels of a tree starts from is 0 indexed, right? Let's look at the root node and recall that the edges is the line connecting nodes in a tree. When you look at the first node, that's the root node, there are no edges, right? There is no edge connecting to it. So the level at that point is 0. But when you get to the direct descendant after it, there is already a edge coming from the parent node. So it's now a level 1. Then when you go down, there are already 2 edges right from the root node to that node. That's the level 2. Then when you go to the last node, there are 3 edges, 3 lines connecting from the root node to that node. Now that makes it a 3-level tree. And we have the first level, which is 0 index, because there are no edges connecting to it. Then we move down, we have level 1. We move down, we see that okay, we now have 2 edges, therefore this is the level 2. And finally we reach the last level, and it can go as as much as level deep as you want, really. And then we also have the subtree. Every root node can be treated as the root node of its own subtree. So basically, if you detach the root of a tree, the highlights, they show that, okay, this is a separate tree on its own. It's once it's detached from the root node, it can act as a root node of its own and still be self-sustained. This can be described as a subtree. Next, we have the degree of a node, and the degree of a node is the number of children of a node. The direct number of children, not the cumulative number of children, but the direct number of children of a given node is the degree of a node. Then we also have other terminologies like the degree of a tree, which is the maximum degree of a node. So when you get all of the degrees of your node, then you get the maximum, and that's the maximum degrees of your tree. We have the width, which is the number of nodes in a level. So we've seen how to calculate the levels of a tree. Now the width is going to be the number of nodes in a level, and the size of a tree is the number of nodes in a tree, all of the number of nodes in a tree. And we also have breadth, which is the number of leaf nodes, that is nodes without children in a tree. Now there are other terminologies, but these are basic terminologies that you would often come across out in the world when you're trying to solve data structures and algorithm problem. They will help you understand the problem when you're finding the maximum depth of a binary tree. Now you know what depth means. You have the some roots to leaf nodes. You understand what a leaf node is. You have counting complete tree nodes. Now you know what a node in a tree means. You know what is required of you. You might not totally be able to solve the problem, but you have an understanding of the terminologies being used in that questions. You have tree order traversal, and you know, okay, you already know what level is. I know traversal means loop, so that means, okay, you want to traverse the levels in a tree, you want to loop over it. Those becomes clearer because you now understand the basic terminologies. Now let's quickly look at the properties of a tree. And we're going to look at two properties that are often used interchangeably, but they are not. The first property we'll look at is the depth of a node. The depth of a node is the number of edges from the root node to the given node. And recall that edge is that line that connects one node to the other. When we are looking at the root node, there are no lines connecting anything to the root node. The root node is just the root node. Nothing is connecting to it, although it is connecting to others, but nothing is connecting into it. Therefore, the edge is 0 and the depth is 0. As we progress down the tree, we start to count the edge and count the depth as it progresses. Next, we move on to the height of a tree. The height of a tree is the number of edges from the leaf node to the root node. Now this is different from the depth, and I understand how it might be confusing. For the depth, we are counting the edges to coming into you, but for the height, we are counting the number of edges going out of you. Now just try to keep that in mind. Depth is counting number of edges coming into you, height is counting the number of edges going out of you. And we can see that the root node has 3 edges going out of it. When we start to dip the height of the tree, it has 3 edges. All of its children has all of these edges, and we count it as inclusive. And as we begin to progress down and down the tree, we see that the depth of the leaf node is going to be the height of the tree is going to be 3, right? Because we have it's going to be 2 rather, not 3, because we have 2 edges coming into it, while its height is going to be 0 because it has no edge going out of it. Now let's quickly look at types of tree data structures, because we also have different types of tree data structure, and we have the general tree structure. The general tree structure is basically just any tree that can have any number of child nodes. It has all of these uses that we've discussed. It has all of these terminologies. Basically, all of the tree structures, regardless of their types, they have similar terminologies, they have similar operations, but they have different properties. The similar properties will be the height and the depth, but as you will see as we speak more on this, they have different properties, some properties that will be discussed. Now the first type we have is general tree structure, and the general tree structure can have any number of nodes. Then we have the balanced tree structure. The balanced tree structure has equal number of nodes, or if there are if there are no equal number of nodes, the difference cannot be greater than 1. This is not a binary tree. The one on the right is not a binary tree, because the difference in the number of nodes from the left child and the right child is greater than 1. For the left subtree that has the target height of balanced tree, the difference is just 1. The difference between the left and right subtree is 1, but an imbalanced tree structure would have more than 1 difference between the left and right subtree. Next, we have the binary trees, and binary trees are trees that can have a maximum of 2 children. This is very different from the general tree structure, where it can have as many children as it wants. And I think this is something like a family structure, basically. Family structures, file systems, even a company, right, can have any number of tree structures. These are general tree structures. When we talk about binary tree structures, they have a maximum of just 2 children. And then we also have the binary search trees. Binary search trees differ from binary trees in that they have a special property where the children on the left, or the values of the left nodes, must be less than the root node, and the values on the right node must be greater than the root node. And this property must work for every subtree as you progress down the tree. Every subtree as you progress down the tree. Once you look at 8, the left and right children, 3 is less than 8, its right child 10 is greater than 8. You look at 3 as a subtree, its left child 1 is less than 8, and its right child 6 is greater than 8. So this is the property of a binary search tree. And a binary search tree is really important in implementing search and sort algorithms, which we are going to discuss in depth. After this general information about tree, we'll be discussing binary trees and binary search trees in details, including their code implementation. Operations of tree data structures. These are common operations that you can perform on all tree data structures. This is insertion. You can insert a value into a binary tree, obviously, and this, we can also create a tree data structure. In fact, before we insert into a data structure, we should have created a tree data structure. And like I mentioned earlier, a tree data structure is going to have this object structure where it has its own value, then it stores its address to its left and right child, and this is how it keeps the connection intact, because there is this links to it, right and left child. Then we also have a traversal. Traversal basically means loop. We can loop through a data structure, and there are 2 major ways of looping through tree data structure. This is the breadth first search and depth first search. Breadth first search is a level order traversal. Recall, level order is level where we are going from the first step to the next step. We have all of the edges together. That's the level order. Recall our definition of the level order, right? And breadth first search says that we are traversing our tree in order. So we are going to start the traversal from the root node. After the root node, we move on to the next level. We get 550. Move on to the next level. We get the values. Move on to the next level. We get the values or manipulate whatever we want on the data, right? Probably we want all of the values that is less than this, all of the values that is greater than this. Whatever we want to do, we can. But this is our breadth first search allows us to traverse through a tree. Then we have the depth first search traversal. This is where the height or the subtrees are traversed first. Just like the name, we are going depth first. So once we start from the roots, we start from the root of the tree. Now, rather than going to the next level, we are going to pick a subtree, either the left subtree or the right subtree, and traverse that in depth. And for the sake of this video, I'm going to picking the left subtree. So we pick the left subtree, we go down that path again, and we can see that okay, there is nothing else for us to traverse here. So we circle back and go to the right subtree. When we go to the right subtree, we are already at that point where this is a subtree. Now we can choose to either go left or right, and whichever we choose to go, we go there in depth. So let's say we choose to go to the left and we pick out that number, then there is nothing else to traverse again, so we circle back and visit the right subtree of that subtree, and then we pick the left subtree, and since there is nothing else to circle back, we are done. We went depth first. We went from the left subtree, we went down till we hit a dead end, then we moved all the way to the right subtree. And depth first search also has different ways of traversal, like different properties that you may want to traverse. And the first way is called the pre-order traversal. The pre-order traversal follows this rule, that is roots, left, right. The way we traverse in our depth first, we traversed the root, we went to the left subtree, then when we did at the left subtree, then visited the right subtree. This operation is called a pre-order traversal, where we are traversing the roots first, we are traversing the left child, then we traverse the right child. We also have the in order traversal, which traverses the left subtree first, visits the node, and then traverses the right subtree. This sort of looks like a triangle if you picture it. Then we have the post order traversal, which traverses the left subtree first, right subtree next, and traverses the root of the subtree. We are going to visit these traversals in depth. We are going to write the code and see the differences when we discuss our binary trees and our binary search trees. So stay tuned for those videos. Thank you so much for watching, and I hope this video was helpful.